In this video tutorial, we will discuss the organic nomenclature of cyclic hydrocarbons and aromatic compounds. Up until this point, we've been focused on simple straight-chain hydrocarbons. However, these alkane and alkene chains can form ring structures known as cyclic hydrocarbons. That being said, due to the linear or rigid nature of the triple bond, cyclic alkynes are often rare and very unstable. Now, many biologically important molecules are based off these ring structures, such as estrogen and testosterone. So it is important that we know how to name these ring structures. Now, as I mentioned previously, I can't teach you every single possible permutation when it comes to organic nomenclature. As such, it is very important that you be able to look at the name of the organic compound, be able to dissect the name, and try to find meaning from it. So what I'm going to ask you to do is take a look at these answers over here and try to match up each of these names with the molecular structures you see on the left-hand side. From there, you will try to identify the rules that govern the nomenclature of simple cyclic hydrocarbons. So press pause and match up these names with the structures on the left. If you are having difficulties, you can always look at the answers at the bottom. And when you're ready, press play and we will take up the answers together and try to come up with some grammatical rules when it comes to naming cyclic hydrocarbons. All right. The first structure corresponds with the name cyclohexane, option B, while the second structure corresponds with cyclopentane, option C, and finally the third structure corresponds with cyclopropane, option A. So based on your answers, what is the grammatical rule you can infer regarding the nomenclature of simple cyclic hydrocarbons? Hopefully you notice that the prefix cyclo was used for every single one of these scenarios, and that is to tell the reader that it's a ring structure. Then the rest is just as we learned in our previous lesson. Prop, meaning that there are 3 carbons, so 1, 2, and 3. Hex, meaning there are 6 carbons, 1, 2, 3, 4, 5, and 6. And then pent, meaning 5 carbons, 1, 2, 3, 4, and 5. So the new grammatical rule is that the prefix cyclo is used to tell the reader that this hydrocarbon has a cyclic or a ring structure. And as we learned previously, prop means that there are 3 carbons in this ring, 1, 2, and 3. Hex means that there are 6 carbons in this ring, 1, 2, 3, 4, 5, 6. And pent means that there are 5 carbons in this ring, 1, 2, 3, 4, 5. Alright, let's move on to the next example. What I want you to do is pause the video and try to match up these names with the structures above. Once again, if you're having troubles, answers are at the bottom. When you're done, press play and we will try to understand the grammatical rules for why these names match up with these structures. So in the first example, we have a cyclohexane. Cyclo meaning it's a ring structure with 6 carbons on it. So here's my ring structure with 6 carbons on it. There is a methyl group, methyl meaning 1 carbon. So there's the 1 carbon. There's an ethyl group, meaning there's 2 carbons. So there's 1, 2 carbons. And there's a butyl group, meaning there's 4 carbons, 1, 2, 3, and 4. So the question now is, how do they choose these address numbers? In our previous examples with straight-chain hydrocarbons, we could either choose left to right, 1, 2, 3, 4, 5, 6, 7, 8. Or we could count from right to left, 1, 2, 3, 4, 5, 6, 7, 8. And then you would choose the counting direction that had the lowest address numbers for your branches according to the rule of first difference. But with a ring structure, there is no natural beginning, there is no natural end. I can start here and count in a clockwise direction, or I can start here and do a counterclockwise direction. Or I can start here and go counterclockwise or clockwise. So if the starting point and the direction of counting isn't clear, what should we do? Well, the rules are still the same. Choose a starting point and a counting direction that gives you the lowest possible address numbers. So if I chose this as my starting point and went clockwise, the address numbers would be 2 for the methyl group, 3 for the ethyl group, and 6 for the butyl group, 2, 3, 6. But obviously we can find a much smaller address number than 2, 3, 6. I could start here and go clockwise to get 1, 2, and 5 as my address numbers, which is better than 2, 3, 6. But even though 1, 2, 5 is better, I think we can go even lower than 1, 2, 5. If we start here and go counterclockwise, my address numbers are now 1 for the ethyl group, 2 for the methyl group, and 4 for the butyl group. 1, 2, 4 is better than 1, 2, 5. And that is how we choose our address numbers. So 4 is where you'll find the butyl group. Number 4 carbon is where you find the butyl group. Number 1 is where you find the ethyl group. Number 1 is where you find the ethyl group. Number 2 is where you find the methyl group. And then cyclohexane. In this next example, we have cyclopentane because it's a ring structure with 5 carbons in it. And the lowest possible numbers you can get are 1, 2, and 4, where the methyl groups are on carbons numbers 1 and 2. So methyl group on the 1 and the 2, and that's why it's 1,2-dimethyl. So there's the di prefix, saying there's 2 of these methyl groups, and they're located on the number 1, 2 carbon. And coming out from the number 4 carbon, we have an ethyl branch popping out. Ethyl meaning that there's 2 carbons inside of it. Now, I did choose to start from this methyl group, 1, 2, 3, 4, 5, counting in the clockwise direction. But I also could have started on this methyl group over here and counted in the counterclockwise direction, 1, 2, 3, 4, 5. But in both cases, you would still end up with the same number, 1, 2 for the dimethyls and a 4 for the ethyl group. So it doesn't really make a difference if I chose the red counting direction or the purple counting direction. Now for the final example, we have a cyclohexane. It's because there's a ring structure with 6 carbons inside of it. We also have an ethyl branch with 2 carbons inside of it, and a methyl branch with 1 carbon inside of it. With regards to counting direction, I could start here with a 1 and a 2 going in this direction. But I could start also with the ethyl branch going in the other direction, 1, 2. So in a situation like this where both counting methods result in the same numbers, we need a tiebreaker. With all things being equal, the ultimate tiebreaker is alphabetical order. So we give the branch with the alphabetical superiority, so E comes before M. Ethyl should get the lower number, while methyl gets the secondary number. So the purple counting direction is correct, and the red one is incorrect, giving us 1 for the ethyl branch and 2 for the methyl branch. So let's come up with a grammatical rule based on the examples we just took up. If simple cyclic hydrocarbons do not have terminal carbons, so they have no natural start or end points on the parent chain, how are the address numbers and side branches assigned? Well, choose a starting point and counting direction that will result in the lowest address numbers for your branches while following the rule of first difference. In the event that both counting directions result in the same address numbers, what can be used as a tiebreaker? Well, alphabetical order can be used as that tiebreaker when the counting directions are equal. So give the alphabetically superior branch the lower address number. Now keep in mind, mono, di, tri, these prefixes, they don't count towards alphabetic order. So in this case up here, we see dimethyl. Well, the di does not count. You have to go straight to the first unique letter, which is methyl, so M for methyl. So don't think that D comes before E, so dimethyl should go first. No. It must be the first unique letter, and the unique letter over here is the methyl, M, and M comes after E for ethyl. All right, let's keep going on. So when a carbon chain is longer than the cyclic hydrocarbon, so if the carbon chain is longer than the ring structure, how is the parent chain selected? Looking at the name, we see butane is in the parent chain position. So it looks like whoever's the longer carbon chain would be the parent. Here they use the term cyclopropyl, cyclo because it's a ring structure, and propyl because there are 3 carbons, 1, 2, and 3 carbons in this ring structure. Then they write 1 cyclopropyl because they need to tell you, the reader, where is this ring structure located. Well, it's located on the number 1 carbon. That's where this ring structure is sprouting out from. If instead of 1, they had used the number 2, then it would look something like this, where on the number 2 carbon, the cyclopropyl branch pops out. You'll also notice that over here, they call it cyclopropyl with a YL to show that it's a branch and no longer the part of the parent chain. All right, so when a carbon chain is longer than the cyclic hydrocarbon, how is the parent chain selected instead? Well, if the straight chain contains more carbon atoms than the ring structure is demoted. A YL suffix, so over here cyclopropyl, is added to indicate that it is a side branch now. But what happens when multiple bonds are located inside the cyclic hydrocarbon? How does this affect the counting direction? So let's dissect the name and try to come up with a grammatical rule for this scenario. First, you'll notice that the parent chain is cyclopenta, so the ring structure contains 5 carbons, 1, 2, 3, 4, 5, which is longer than the other side branches, so therefore this must be the parent chain. Next, you'll notice the suffix diene to say that there's 2 of these double bonds located over here. You'll notice that the address numbers for these double bonds are on the 1 and 3 carbon. So I can start at this carbon and count counterclockwise, 1, 2, 3, 4, 5. That way we have a 1 for the double bond location and a 3 for the double bond location. Or I can start at this carbon over here and make this my carbon number 1, but count in a clockwise direction, 1, 2, 3, 4, 5. And again, we have the 1 for the double bond and the 3 for the double bond location as well. Since both the counterclockwise and the clockwise counter directions give me a 1, 3 for the address numbers of the double bond, 1, 3 for the address numbers of the double bond, I'm going to need a tiebreaker. With the red counting direction, my address numbers for the branches are 3 for the methyl and 5 for the ethyl, so 3 and a 5. But with the blue counting direction, the address numbers for my branches are 2 for the methyl and 5 for the ethyl. 2, 5. So at this point, we're going to have to use the rule of first difference. Since 2 is the lower number than 3, the blue counting direction is correct, and we have to eliminate the red counting direction. But what if, instead of a 3, this had been a 2? In that case, they're both identical, so we would need another tiebreaker. And if all things are the same, it's usually going to be alphabetical. So give the ethyl group, begins with the E, versus the methyl group, M. Ethyl group should get priority at that point. So this naming system is very systematic and not as bad as you imagine it to be. But let's go back to this example. We are going to use the blue counting direction. So the location of our double bonds is on the number 1 carbon and the number 3 carbon. So that's why it says 1,3-diene. With the ethyl branch located on the number 5 carbon, so 5-ethyl. And the methyl branch located on the number 2 carbon, so 2-methyl. Putting it all together, we must assemble it alphabetically. E comes before M, so it goes 5-ethyl, 2-methyl, cyclopenta 1,3-diene. So, to summarize, when multiple bonds are located on the cyclic hydrocarbon, how does this affect the counting direction? Double bonds have higher priority than branches, so give them the lowest address numbers. If a tiebreaker is still required, choose the direction that assigns branches the lowest numbers according to the rule of first difference. And if you need another tiebreaker, go with alphabetical order when assigning lowest numbers. For our final example, it can look a little confusing at first, but if you've been paying attention up to this point, I would say 75% of this name you already understand. And there's really only one small portion here that may be a little confusing. So let's start off with our parent chain, which is always found at the end of the name. It says cyclohexa, which means they've chosen this ring structure with 6 carbons inside of it to be the parent chain because A, it's got the double bonds located in here, but also B, it's got the most number of carbons located here as well. Yes, there's a double bond up here, but there's only 1, 2, 3, 4 really carbons involved before you reach the ring structure. So because the ring structure has more carbons than this branch over here, even though they both have double bonds, this one gets higher priority because it's got the double bonds and more carbons than these other side branches. Now over here, they have identified the address numbers of the double bonds. Since there's 2 of them, it says diene, 2 double bonds, and they're located on the number 1, 3 carbon. So I could start here and count in a counterclockwise direction, 1, 2, 3, 4, 5, 6. Or I could start on this carbon and move in a clockwise direction, 1, 2, 3, 4, 5, 6. In both cases, my double bond is located on the 1 and 3 carbon. So 1 and 3, or 1 and 3. So again, I'm going to need a tiebreaker. With the blue counting direction, the address numbers for my branches are on the 3 and 6 carbon. So 3 and 6. While the red counting direction has a 2 and a 5 for the address numbers of my branches. According to the rule of first difference, 2, 5 is better than 3, 6. So we're going to go with the red counting direction. Becoming 1, 3 diene for the location of my double bond. So on the number 1, there's a double bond. On the number 3, there's a double bond. Because there are 2 of them, we put the di prefix. We then have a methyl branch on the number 2 carbon. So it's 2 with a methyl branch. And then on the number 5 carbon, we've got this weird thingy that I put in brackets. So on the number 5 carbon, I've got this weird thingy here that I put into brackets. As I mentioned earlier, 75% of this structure you already understand the naming system for it. It's just this one little portion over here that's going to require some additional explanation. But even within this new part, you should be able to understand some of it. So let's take a closer look. It says bute. Bute means there are 4 carbons. And that's exactly what we have. 1, 2, 3, 4 carbons in this bracketed area. Bute. So check mark, we understand that part. Now it says 3En to show that there's a double bond located on the number 3 carbon. That's what happens. On the number 3 carbon, a double bond sprouts out. So that's nothing new. That should also make sense. The strange part is this one over here. Now, we had previously mentioned that the YL suffix means that it is a branch, and that is what this whole portion is. It's a branch coming off of the main parent chain down here. And the purpose of this number 2 is to tell the reader where is it attached to the main chain. If instead of 2Il, they had instead written 1Il, then that would mean this bracketed portion would be attached to the parent chain on the number 1 carbon itself. But because it says 2Il over here, then it is attached to the parent chain on the number 2 carbon instead. So that's the purpose of this little block over here, 2Il, to tell the reader where is this weird branch attached onto my parent chain, or connected to my parent chain anyway. So if you want, you can think of it as a kind of an umbilical cord, right? Where is the branch attached to the parent chain? Well, over here we have a number 2, and that is the attachment site to my parent chain, the umbilical cord that latches on or connects it. If it had been a number 1 instead, then the attachment point, the umbilical cord, would have been on the number 1 carbon. All right, so that brings us to our last point. What is the purpose of this bracket? The reason why we need this bracket is because there are 2 numbering systems in this structure. There is a numbering system in red for the parent chain, and a numbering system in blue for the branch. So all the numbers outside the bracket, such as the 5, the 2, the 1, and the 3, all refer to the carbons within the parent chain. Meanwhile, everything within the bracket in blue refers to the numbering system in the branch itself. Because there are 2 numbering systems, we do require the brackets to help the reader differentiate between, well, this 3En. It says there's a double bond located on the number 3 carbon, but are we talking about this number 3 carbon on the parent chain, or are we talking about this number 3 carbon on the branch itself? If the bracket was not there, I wouldn't be able to tell whether I want the reader to draw a double bond on the number 3 carbon on the parent chain or the number 3 carbon on the branch itself. Now, you may also notice that we did not count right to left, we only counted left to right. Normally we would give the double bond higher priority and give that the lower number, so you would go 1, 2, 3, 4 within this branch and count right to left. But it's the umbilical cord, the attachment site to the parent chain, that gets higher priority than the double bond. Since the attachment site to the parent chain must get the lowest number, I'm not allowed to count right to left, otherwise it'd be a 1, 2, 3 Il, and this would be a 3Il, attachment site to the parent chain. But of course, 1, 2Il is much lower than 3Il, so we have to count left to right instead, and the purple numbering system is incorrect. And that's how we chose the counting direction within the branch itself. Make sure that the attachment site to the parent chain gets the lowest possible number, no matter what else is bonded inside here. Okay, so let's summarize all the grammatical rules we just learned. How was the starting point or counting direction chosen? Well, exactly the same way we've done previously. Choose a starting point and counting direction that provides the multiple bonds with the lowest possible address numbers. And of course, if a tiebreaker is required, assign branches with the lowest numbers according to the rule of first difference. If you still need another tiebreaker, go in alphabetical order. What is the purpose of the brackets? When multiple numbering systems are being used, the brackets are there to help the reader distinguish, or at least separate, between the numbering system in the parent chain versus the numbering system within the branch itself. So numbers outside the bracket refer to the parent chain, whereas numbers inside the bracket refer to the branch. What is the purpose of the underlined component in but 3En with a 2Il? So what's the purpose of this little suffix here, 2Il? It is used to identify which carbon in the branch is directly attached to the parent chain. So as I call it, the umbilical cord. Where is the attachment site to my parent chain? Now that we've covered ring structures, we can take it one step further and look at aromatic hydrocarbons. These compounds initially refer to those responsible for the strong odors of plants. So chemists in the perfume industry would focus on these aromatic compounds, as these smells and fragrances could be used in their perfumes. While researching these compounds, they found that they tended to have a low carbon to hydrogen ratio. If you'll recall, the general formula for alkanes is CnH2n plus 2, so C3H8 would be an example. The general formula for alkenes with double bonds is CnH2n, so C3H6 would be an example of that. And finally, alkynes had a general formula of CnH2n-2, so C3H4 would be an example of this. As you can see, the ratio of hydrogens to carbons is getting lower and lower and lower. So with the understanding that these aromatic compounds have a low carbon-hydrogen ratio, they assumed that they would contain double bonds and triple bonds. But there's a problem with that. Multiple bonds, such as doubles and triples, tend to make compounds more reactive, but aromatics are known for their unusual stability. Now, the chemical formula for benzene, C6H6, was well known in the mid-1800s. Unfortunately, no one could determine its structure. Many chemists tried different variations of singles, doubles, and triple bonds, but no one could come up with a structure that matched the properties of benzene C6H6. That is, until 1865, when Friedrich August Kekulé von Strandnitz comes along and he dreams of a snake swallowing its own tail. This was when he realized that benzene wasn't some kind of straight-chain hydrocarbon. Instead, it was a ring structure. This new way of thinking meant that organic structures were no longer limited to straight-chain hydrocarbons. Now, one of the reasons why no one could come up with a structure that matched up with benzene's properties is because benzene doesn't actually have single or double bonds within it. Instead, experiments show that every bond within the benzene ring is identical. To explain this, the concept of resonance is used. In such cases, the electrons are delocalized and equally shared amongst each bond. This provides greater stability because the electrons are not readily available for chemical reactions. So when you draw benzene, you could do it like this, or you could draw the double bonds over here like this. However, neither of these drawings is accurate. Instead, it is an average of these two structures. And quite often, benzene is drawn with a ring within the hexagon to show that these double bonds don't actually exist in one location, but are instead spread out and delocalized. If you look at benzene, you can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds divided amongst 1, 2, 3, 4, 5, 6 regions, giving it an average bond energy of 1.5. So not quite a single bond and not quite a double bond, but something in between. So aromatic hydrocarbons are those that contain a benzene ring. Up until this point, we've been dealing with aliphatic hydrocarbons, those that do not contain a benzene ring, those that are not aromatic. When it comes to aromatic nomenclature, if you put two benzene rings together, we call that naphthalene, which is the active ingredient inside of mothballs. I don't see these being used too often today, but my grandparents' house smelled of mothballs. Many of their clothing were made of cotton and wool, and naphthalene is a pesticide that would kill the insects that would eat and damage their clothing. So whenever I smell naphthalene or mothballs, I think of old Chinese people. Anyway, combining three benzene rings together, you get anthracene, which is often used in dyes, plastics, pesticides, wood preservatives, so many applications. As a matter of fact, benzene is a very important starting point for many organic chemical reactions that produce materials that we use on an everyday basis. That being said, for the purposes of this course, we will only concern ourselves with a single benzene ring. So let's take a look at these three examples over here and how their names match up with their structures. This in turn should better help you understand the grammatical rules that are used when naming aromatic compounds, specifically those that are based off of a single benzene ring. In each of these three examples, benzene is the most important part of the compound, and so they've chosen to use it as the parent chain, which means that it must be at the very end of the name. When benzene is the parent chain, just call it benzene. Benzene, benzene. Looking at our first example, we must choose a starting point and counting direction that gives priority to the branches. Normally, if this was just an aliphatic ring structure, we would have to give priority to the location of the double bonds. But because benzene does not have any multiple bonds, instead the electrons are all delocalized, every single bond within benzene is the same, and no particular carbon is more important than the other. So let's just focus on the location of the branches. Starting at this carbon and counting in a counterclockwise direction, you get 1, 2, 4 as the address numbers. And I don't believe there's a better counting direction that will give you a lower number than this. As such, carbons 1 and 2 contain your methyl groups. Because there are 2 of them, you call it dimethyl, 2 methyl groups. Meanwhile, on the number 4 carbon, an ethyl branch is sprouting out from here. Putting it in alphabetical order, E comes before M, so remember the di prefix does not count towards alphabetical superiority. All right, so methyl, M, ethyl, E, ethyl comes first, so we get 4-ethyl 1,2-dimethyl benzene as the name for this structure here. Looking at our next example, you will see the presence of brackets, which tells the reader that there are 2 numbering systems involved, 1 numbering system inside the branch, while the numbers outside the bracket are for the parent chain. Again, we will use the benzene ring as our parent chain, and again, we'll start from this carbon and count in a counterclockwise direction to give us the lowest possible address numbers for our branches, because there are no double bonds to give priority to in the benzene ring. On the number 1 carbon, we have a methyl branch. On the number 2 carbon, we have an ethyl branch. While on the number 4 carbon, we have a bracketed area to show the reader that there is going to be a new numbering system here. But why do we need a new numbering system? Because we need to tell the reader where the triple bond is located. Currently it says it's located on the number 2 carbon with the attachment site to the parent chain on the number 1 carbon. That's why it says 1-il. Thus this branch is numbered 1, 2, and 3 going from left to right. The other option would have been to put the triple bond over here between carbons 1 and 2, and we would have to change this 2-in into a 1-in instead to tell the reader where the location of the triple bond is. So because the triple bond could be in 2 different locations, I need to tell the reader exactly where the triple bond is located, which is why we need another numbering system to tell the reader and help them differentiate between a 2 carbon over here versus the 2 carbon down here. Where should the triple bond be? Should the triple bond be on this number 2 carbon or on this number 2 carbon? By putting a bracket in this area, I know that we're talking about the number 2 carbon of the branch and not the parent chain. Alrighty, so remember, brackets are used when there are 2 numbering systems to help the reader differentiate between which carbon number you're talking about, those within the branch, within the bracket, or those outside the branch or on the main parent chain, outside the brackets. So on the number 4 carbon of the parent chain, we have a 3 carbon branch, that's why it says prop, 1, 2, 3, where the triple bond is located on the carbon number 2, so on the number 2 the triple bond sprouts out, and then on the number 1 carbon, 1-il, to show that on the number 1 carbon we are attaching to the parent chain. Alright, moving on to the last example. You'll notice over here that we've kept benzene as our parent chain, even though this straight-chained aliphatic component has 8 carbons, so more carbons than the 6 that are found in benzene, the benzene ring is still more important than this component over here. This benzene ring has a greater impact on the chemical and physical properties of the molecule than this component over here. As such, there will be 2 numbering systems, one for the parent chain and one for the branch inside the bracketed area. Alright, so benzene is the main parent chain, so it goes all the way at the very end. Meanwhile, the branch has 8 carbons in it, which is why it's oct. There is a double bond coming out from the carbon number 7, so 7-ene, 7, then here's the double bond location. And then 3-il to tell the reader that on the number 3 carbon, that's where we're attaching back to our parent chain, 3-il. And on the number 5 carbon, there's a methyl branch popping out, methyl branch right there. For the branch, they chose to count from left to right because the attachment site to the parent chain is more important than the double bond or the branches, so 3-il is the lowest possible number I can give to the attachment site. Now, a common question students ask is, why do we have this red numbering system over here when it's not located in the name itself? What's the purpose of the brackets if you don't actually have the second numbering system? You could put the 1 in front over here to tell the reader that from the number 1 carbon, this branch area pops out, but it's not necessary because for this molecule, this must always be carbon number 1. There is no other choice. If I took this whole branch and stuck it onto carbon number 3 over here, well, this carbon would not be carbon number 3 anymore. Remember, I have to choose the lowest possible number. So now this 3 would become my new starting point, and it'd be my new carbon number 1. If I taken this whole thing and shoved it onto this carbon instead, of course. So for this example, wherever this branch is attached to, that would be your carbon number 1. So the number 1 here is not really necessary. That being said, if you did include this on a test, I don't really care. It's not a huge issue and I'm not super concerned about it. But of course, please check with your teacher or professor as they may have different requirements. Now, since the branch is popping up from this carbon over here, let's number it properly and keep it as carbon number 1. All right, there you have it, aromatic nomenclature.